of a heated sample or a welded sample. The purpose of this experiment is to analyze the microstructure of two samples, which is a high to low carbon sample and a low to low carbon sample, and also correlating each zone in the sample with a microstructure. So there are going to be 5 zones which are going to be analyzed in this situation. The first zone is going to be the zone which is not affected by heat. The second zone is the heat affected zone, and that leads into the welding area, which is the coarse grained heat affected zone. And so the third zone is going to be the fusion zone, where the welding actually takes place. The fourth zone is going to be the fusion line, and the fifth zone is going to be the heat affected zone to the left of the welded area. And lastly, we can talk about the original structure of the sample. So, beginning of the lab, all you gotta make sure is you have the safety goggles. Your shoes should be tied and closed-toe shoes. Is that what it is? Full sleeves and no loose chains. Or before we begin, I'd like to talk to you more about how the process of welding actually takes place. Welding is just a fusion of two materials or samples. In this case, steel with each other. So by using high heat, we melt the steel and then we fuse them with the other part of this sample. So in this case, you can see this area right here is actually a welded part, with another steel with variable amounts of carbon. Alright, so before you start any experiment, everyone has to make sure that safety is always first. To ensure your safety, you have to wear safety goggles. What else? Okay, you have to wear safety goggles. Your sleeves should be no loose sleeves.
Hi, my name is Mohammed, and I'm going to, this is the first process of the welding, which is hardness. So we have two machines right here. One is Rockwell C for the harder material and Rockwell B for the softer material right there. And the Rockwell C for the harder material, because we start with the Rockwell C first for the harder material, then we go to the B for the softer, because this has the tip of diamond. And for the process, we just put this piece here in the face right here, and then this, like, we have all the old tests down here, so we have to keep it like around 0.25 away from. A quarter of an inch away from those, so we can have a better result. So for that, what we do is like place here properly, and then just take the piece up there. And before that, we have to make sure this load always has to be up here. So it's like minor load, like, you know, it has to be right here. And then what we do here is we check, and we have to make sure this is at the black dot right here, and it has to be +5 or -5. It's all good. And we have to make sure that this is 0. We have to set it to 0 so we can have a thing and go. We have to look around how many zeros it goes there, so we can, if it's like more than 1 and then it comes back, so it has to be 0, we just take the stuff like that, and then we have to wait until it stops, the needle stops right there, and we just pull it back, so get the result. And this needle didn't pass through again, like once, so it means there was 100, it passed through 0 before and another 1, so it means we just take the reading as it is. And right now the reading is, for the C1 we take is like, it's almost 10. So we just take that. So, and this is the low side, so that's why it came low. And then if we do the same thing for in the middle part, and it's going to be harder at the fusion. It's going to be harder at the fusion because there's two materials, like two low carbon and high carbon, is going to like fusing together, so it's going to be harder. The material is going to be harder at the middle. So the results that we got here is less than 10, and then it describes us that this material is softer. So for that we have to go to the B machine and check how hard this material is, the hardness of this material, and So this is our B machine for the it has the same setup as C machine. So we did the test on this, and the result we got is 96 or 97 for the B scale, and it has. And this is the average of the low, that we got. We're looking for the result we were looking for. We got the same result down here, like average to it.
Hello everybody, I'm Vishwadit Singh. I'm representing Group 4 in the grinding and polishing of this metal sample. Fault safety is #1 priority. So the main purpose of this polishing is to remove all the debris from the surface so that we can have a good image at the microscope, because this, after polishing and grinding, will have a mirror image so that it can reflect the light to a greater extent. And we can have a good view at the microstructure of all of the sample. So I'm explaining you about this machine. It's you can see it's sandpaper. Starting from coarse to a finer one, we will wipe away all the impurities that comes from the surface. So we're gonna start at about a 45 angle so that we can remove more debris from the surface, applying uniform pressure on both sides so we can have a good polishing, a good grinding, just small strokes, applying uniform pressure at both sides. Small time at the coarser ones and more to the end, to the finest. When you go to the next sandpaper, you need to tilt the piece of metal at another, perpendicular to the first one or the other 45 degrees, and do the same process again. As you can see, it's becoming more finer. You can see the grooves on the surface, but it will go after the polishing. This is the most finer one, so I need to spend more time on this, doing gentle strokes, applying uniform pressure, I say, so that we can have uniform grinding. You see the grooves, they are like an X direction at 45 and the other 45, perpendicular to each other, so it's a good grind. After the process of grinding, it's time for the polishing. This is done with the aid of this polishing wheel. Here's it. Actually, it's kind of you can say a moving sandpaper, so it polishes the surface. Let me turn it on. An important thing while using this is not to wear too long sleeves or baggy clothes so they can get entrapped in the wheel. Don't wear any jewelry and necklace, watches or wristbands kind of stuff. So I'm switching on. So now it's moving. Then it's some of this is a polishing agent, alumina, so that we can have a more finer and a mirror finish over the surface so that we can see our own reflection in it. Like I said, to reflect the light of the microscope to a greater extent so we can have a high resolution images. Small amount of it. So as the wheel is moving clockwise, we need to hold our piece and go in anti-clockwise direction so we can have more friction and have more polishing of the surface. Applying uniform pressure with both hands on both the sides, slowly moving it in counterclockwise direction. As you can see, it's nearly perfect. Yeah, you can see this, it's perfect, but now we need to wash it.
Hi, my name's Steve. I'm going to take you to the next process. Once we buff, we got to clean off the excess. We use some distilled water. This has no impurities. Give it a good clean here. Once it's clean, we need to dry it. This is a high watt dryer. You want to use tongs so it gets very hot in your hands. Again. Now that it's dry, as you can see, very shiny, we're going to apply some acid. This acid is actually called nitol. It's only at 2%, but it's still strong enough to clean off any other debris, impurities, oils, anything that might have been on there. This is called etching. We're going to use this liquid for 45 seconds. Basically, The book says it'll take off about 75 microns. If we leave it on too long, it may burn the surface. Using a petri dish to catch any excess. Just put it on there and drop it in. After 45 seconds, we want to use distilled water again. Give it a rinse. We need to dry this and then go to the microscope. This is Steve again. Now we're going to talk about our microscope setup. First, you want to place your piece in the center of the plate. You want to start at your lowest magnification. That way you can get an idea of what you're looking at. Right here, you have your focusing knob. Over here, you have your X and Y axis. So you can see it scrolls over the piece. Now, let's bump this up to times 50. We're going to focus in. Beautiful. Over here, we have an exposure control. What this does is lets more light into the lens. This right here is our camera. Basically, it's a digital exposure, so it opens and closes the lens on here. A little brighter, a little darker.
Hi guys, my name is Noreen, and I'm going to be talking about the grain sizes in between the five sections of the welding. So this is the high carbon. You can tell that it's spaced out, and its microstructure is gathered, and it has large grain sizes. Because of the scatter and the content of carbon is really high in this, you can tell it's going to be a softer material. It is actually the softest area of the section. And you see that, actually we talk about perlite and ferrite. And this is perlite because it's darker. It has a lot of high carbon content. Hi, so this is the left side. We start from the high carbon, so we're moving on to the heat affected zone. So you can see the grain sizes are still large and it is still loosely packed. But because even though it is heat affected, its softness is still, its hardness is still soft. So this part of the sample is the weld zone. You can tell it still has large grain size, but it is closely packed together, and it is a very hard hardness. And you can see a little bit meshing of some other materials too, like sulfur, a little bit of white, and yeah, it is the hardest part. So this part of the sample is the left side, getting closer to the low carbon content. And you can see more white, which is a ferrite. So you can tell that it is closely packed together, and the grain sizes are getting smaller and smaller. Because of the close packed, dense grain structure, the hardness is going to be definitely hard. So this is the last part. It is the lowest carbon, and to the right side. This, you can tell the grain sizes are very small, and you can see a little bit of sulfur here as well, and it is the hardest part of the material. So after capturing all the pictures, you need to save it on the computer. So you click on capture, and then you save it into the computer and use your USB drive. And that is the completion of investigation of weld samples.